Not the header files. The initializer list portion, right? Like if we look back, maybe say at the vector iterator, wherever he's at. Where are you? Const vector iterator, right? If we look like at our constructors, right? All the work is being done in the initializer list portion, right? Very rarely in this class should you have anything being done inside here, but occasionally there will need to be work done here, right? If you don't initialize a variable, if you don't initialize a member variable by the time you reach the inside of this curly brackets, what value has it been initialized to? The default constructor, if it has one, so for any class, it'll be initialized using the default constructor, the 0 argument constructor, right? If it's not an object, if it's not a class, right, it's like an integer or a double, it's undefined what its value is going to be. So it depends on those two situations. So a lot of people are confused, like, what's the point of a copy constructor? And so I'll ask you, what's the point of a copy constructor? What's the point of a copy constructor? And again, this is not a trick question. Its name tells you what it does. It's to create a copy of the object that's passed in, right? That's what it does. So like if we look back here at the vector, wherever you're at, right, we have our vector. Where's this copy constructor? This copy constructor right here. So what should this function do in terms of creating a copy, right? We want to create a copy of a ridge, right? So I somehow have to, initialize my member variables, contents, num elements, and current size, right, to be copies of the original guy that was passed in. Now, for our vector, it's slightly more complicated because of memory that we have here. In most copy constructors, all you need to do is make your member equal the right-hand side's member. And you can do that purely in the constructor, or in an initializer list portion. But over here for our vector, we had to do a little bit more work, because if we made our vector point to the same contents as the other one, we now have two vectors sharing the same location of memory, which we probably wouldn't want to have happen. Right? If here's vector 1 and he has like a size of 3 and a max size of 3, and then here's his contents is pointing to this array 7, 8, 9. If I try to make my copy over here like v2, well, his size should end up being 3. His max size should end up being equal to 3. And then the problem, if we just copied the elements over, right? We said, the new guys equals the old guys, is he would now point to this location of memory, right? So now if I change v2's, so if I do something like this, v2 dot at 0 is equal to 99, what's going to happen? Right? This guy over here changes to 99, and so what's it look like to v1? He changed too, right? So now if I change the copy, I'm changing the original. Would I want that behavior? No. So we had to do this little bit of extra work, right, down here, where I create an entire new array, and then I copy each of the individual elements over. So instead, I had to create an entirely new array of elements, and then copy each value over. We copy over the 7, copy over the 8, copy over the 9. And so now if I change v2, he's now pointing here. Is it going to change v1? No. And so these are some of the things you need to watch out when doing copy constructors. But again, for most of them, 99%, and most of their members, just copy them over to be equal to whatever the original says. Yeah. Like we deleted operator equal on the iterator, I believe. but we didn't delete it on the, we didn't delete operator equals on the vector, but we probably should have implemented our own operator equals as well, so we could allocate that space, right? Shrink to be the correct size or resize to be the correct size, and then copy the elements over. Does that make sense? Because what our operator equals is going to do right now for our vectors is going to set, my contents equals your contents, my size equals your size. And so I end up doing the same thing where we're both pointing to the same object, right? So what I want to do in my operator equals is to resize. You guys want to just write operator equals? Sure. So this is, we made it so our vectors weren't copyable, our iterators weren't copyable, and that's just how we define them. But if we want to overload our operator assignment so that we have that done, where is this? So we have vector reference, come on, operator equals const vector of t reference, right hand side. So what we're trying to do is we're trying to const vector of t reference right hand side. So what we want to do is we want to change ourselves to look like the guy on the right hand side of the equal sign. What should I do? Ooh. So the first thing that we have to make sure is that we don't copy the pointers, right? I don't want to copy, like, my contents point to your contents, right? I want a copy of those elements. So what I need to do is, well, if I was smaller than the original, I should grow to become bigger, right? And if I was larger than the original, I should shrink to become smaller, right? So what I can do is I can call resize, and I want to resize myself to be the right-hand side dot size, right? So I become the right-hand side size, right? Grow or shrink accordingly. And then what should I do? Well, now my, I think we called it like num elements should be equal to the right-hand side's num elements, right? Which I think is taken care of by resize. I think resize will take care of both of those things. Let me just double check. Boop-a-doop, boop-a-doop-a-doop. Okay, yeah, we already taken care of it. So we've updated, resize took care of updating our capacity and size. So now that I've shrunk to become the correct size, what should I do? Not push back, because push back would keep adding more space, right? So then I'd be left with like, well, insert again creates new space. Yeah, just dot at, right? So we could have something like, for int I equals 0, I less than, like we could also have done like an iterator-based for loop too. I less than size plus I, at I is equal to right-hand side dot at I. And then we are going to return ourselves. That's how these things work. And fantastic, we're done. Does this make sense for what operator equals should do in this context? Right, this is like operator assignment, not operator equality. Again, for most of them, you don't need to do this because you just want to copy each one of the members over, right? And if you're happy with each member being like assigned over, like, if we just did something like, my number of elements equals right-hand side number of elements, my capacity equals right-hand side capacity, my contents equals the right-hand side contents. If we were fine with that, we could just let the compiler write it for us, right? But if you need to do something different, like we do need to do here for vector, you have to implement it. It depends on the context of your problem. By default, probably yes. Whenever if you have a pointer to something, right, you create a copy of that object, you might need to create a new instance of the object that you point to and then point to that thing. But again, it depends on the problem, and I can't say 100% of the time that that's what should happen, because there are things where it doesn't. For example, shared pointers, they don't do that, right? Because they still will want to point to that same object. Well, you don't want to increase the reference count, so you need to do a little bit of well, you need to do something a little bit different in the operator equals to affect the reference count for when that shared pointer got pointed to something else. Any other questions here? We got kind of sidetracked, but good discussion anyway. Okay. One other thing that I was thinking of that we probably should have done to make this less crappy, not here, but wherever the heck insert's at. The reason that like this, like a slightly better way that we could have done this is something like int old capacity is equal to size, which I actually want to move down here. And this is going to be a constant old capacity. And then over here, we could do this, or it's not, maybe not old capacity, but old size. Make this be equal to old size. That's all we really need it for. Then we can move the ++ num elements up here, and then we can switch back to using the @I like we were doing before. Because now everything should be in bounds with the correct checking. And if I'm correct in my thinking after class, it should work. Oh, this was not @I, but @pos, right? Oh, I agree. A vector of t reference. There should have been a vector of t reference. Okay, try again after all my mistakes. Woo! Working good. This is what we had right as we left class at the end of the day. One other place we might want to do the out of bounds error is in the iterator. So we might down here do something like pound include vector out of bounds error. And then down here in operator star, right, we can have that same kind of check, like if you're out of bounds, throw the exception, right? But I guess we actually don't even have to do that because calling here will throw the exception if we're out of bounds. So technically we don't have to add anything in here because if we attempt to access and it's out of bounds, we'll end up throwing that exception as well. So I don't need to add anything in here, which is really nice. Does that make sense? Or we don't have to add anything explicitly there, and we can just rely on the method to take care of us. Guys either all seem overwhelmed or very bored. If I go with the very bored option, we're going to jump into C. But if we're overwhelmed, what's your question? Yeah. Yeah. Okay. Back here, if we look at we call verify in bounds, and verify in bounds, if it's out of bounds, we'll throw an exception. So yeah, if we call and throws an exception, we end up throwing that same exception as well because we don't attempt to catch it. Also, bounds already ++. You wrote it.
I wrote that too.
You wrote that today in class, yes. Anything else? Twice. 3 times. Okay, we're on to C now. So if you thought moving from Python to C++ was bad, moving from C++ to C is probably a little bit worse. I know. So C is actually a subset of C++. So you actually already know a lot of it, so you can be happy about that. But since it's a subset, there's going to be some stuff that's missing. The things that are missing are the standard template library. So everything that started with std::, that's gone. We cry, right? No vectors, no maps, no sets, no strings, no anything, right? That's all gone. There are no more references, only pointers. There's no new and delete anymore. There are other functions used instead. There's no for each for loop. The only for loop that exists is the index-based for loop. There are no namespaces and function overloading. There are no exceptions, there are no classes, there's no operator overloading, and there's no templates. Yeah, there's no classes. Right? So you can see that writing C-style code is going to be quite a bit different because a lot of the stuff you've been relying on up until now just does not exist anymore in C. And so things get a little bit more challenging. So even though there's no STL, there are some still standard functions that exist in the C library. If you were using them in C++, you would pound include something that started with a C. So pound include C stdlib, C stdio, cmath, etc. In C now, to include these files, it's pound include stdlib.h, stdio.h, math.h. Remove the C, add .h. So IO, again, there's no C in and C out because what do those start with? std, right? So those are gone. So the functions that you're going to use instead are printf and scanf. And the syntax they have is they both return integers. They accept a format string for what the output should look like, and then the variables that you want to fill into that format string. Scanf, though, is reads out from the standard input. The format string controls what's read written. It can hold literal values, things that are displayed or read exactly as they're written, or placeholders, which are going to hold a place for a variable. So all the placeholders begin with a %sign. So %C is for character, %D is for integer, %U for unsigned integer, %F for float, %LF for double, %S for string, and if you just want a plain old %sign, it's %%, right, to escape that % meaning. And when you list these placeholder variables, there need to be at least as many placeholder variables as there are variables that show up later on. So over here, if we had like age and height, so we said like enter your age using printf, we do scanf %D into the address of age. The scanf function needs pointers to the locations in memory where you want to store the result. Printf, you just give it the variables you want to display. So down over here, we ask for the height, so we read it in as a double. And then we say, you are this many years old and you're this many centimeters tall. And then the variables that we fill in, they get filled in order. Age gets filled into the %D, height gets filled into the %LF. Any questions here so far? Yes. I'm not using references. What does the ampersand in front of a variable mean? Address of, right? When does the ampersand mean a reference? When it appears after the type declaration. So like int ampersand x equals, right? Or like vector of t ampersand v equals, right? That's when you're declaring a reference, right? It's type ampersand. Ampersand variable is the address of the variable, right? It's something people get confused with all the time, so don't worry about that. Just pay attention to, is it appearing after a type or in front of a variable? After a type reference, in front of a variable address of. Any other questions here? Okay. So printf will return the number of characters that you actually wrote to the screen, and scanf will return the number of format placeholders it was able to fill in. This is super useful if you want to check to see if you've received valid input, right? So here we might have some prompt that we want to display to the user. Then we have an integer that we're trying to read val, and then this num_args, right, is the number of arguments that we're actually able to read. So we do display the prompt. We print that out to the screen. Then we attempt to read a single integer from the user, storing the result into val, and numargs_read will either be 1 if I was able to read an integer from the stream, or 0 if I wasn't able to read anything, right? Because I could either read it or not. And if there were a couple of different things like %d, 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 like 3% d's, I could either get 0, 1, or 2 back, because I could have either read 1 of them, 2 of them, 3 of them, or none of them. So as long as it's not equal to 1, keep asking over and over and over again until they enter an integer. There's some stuff here that's wrong, and that this will actually cause an infinite for loop, but we'll try to get into input validation a little bit better in a little bit, probably next week. But any questions here about what scanf returns? Yes? Oh, well, I think I forgot a curly bracket here. Like that. Any other questions? Okay. So literals in the scanf format string, white space in the scanf format string matches 0 or more white space characters. This is really useful for reading non-white space characters because %c will read white space characters. So like, if you ask the user to say like enter a letter and they type space A, you would get the space if you just had %c, not the A. Whereas unlike in C++, when you read into a character, you get a non-white space character always. So what you can do is you can put a space in front of that %c. That space will match with all the white space that's in front of it and read it all up. And then you'd end up getting the first non-white space character because space only matches with white space. Matches with 0 or more white space characters. One mistake that people sometimes make when they start using scanf is to add a space or a new line character at the very end of the scanf statement. This is going to cause a lot of weird behavior in your program because if you put a space at the end, right, space matches with 0 or more white space characters. So the user will keep pressing enter and they'll go forever because space keeps matching and they'll be stuck. If you put a /n at the end of your scanf string, you'll first match when the user presses enter, that /n will match with the first /n, and they press enter again and then you get the second thing. So make sure there's no white space or /n's at the end of your scanf string. It'll be really weird. Other literal characters can appear in the input, but they don't have to store. So they have to appear like in the position that you do. So over here, we ask the user to enter in like their initials with periods in between each letter. So I read a non-white space character. Notice there's a space here. If I didn't put a space here, I could actually read in white space as their first initial. Then they have to enter in 0 or more white space characters, followed by a period, followed by 0 or more white space characters, followed by a letter, followed by 0 or more white space characters, followed by another period. And if it doesn't match that, the scanf statement won't be happy. Does that make sense? So scanf is looking for exactly that. Any questions here about what the white space means? Or the periods? The periods mean I literally want to read a period, but I don't want to store it anywhere. But if they enter something that's not a period, the reading will stop. Cool here? Yeah. You could view Bob, hello, whatever, right? If you put like hello right here, the user would literally have to write in hello before we'd be able to continue reading. So it can be as complicated as you want. So we'll probably pop back to input a little bit later next week. But again, there are no references. But what can you use instead of references? Pointers, right? So you're going to be using a lot more pointers over here in C because you don't have references. And again, I'll put this statement down. I'm going to repeat it twice. Make sure you ask me if you have questions on it. But if inside your function, you would like to be able to modify a variable of type x, you must at least pass a pointer to x's type. So if you would like to modify an integer inside your function must accept a integer pointer, right? A pointer to the type you want to modify. If you want to modify a character, your function would have to accept a character pointer. If your function wanted to modify a float, it would have to accept a float pointer, right? If it wanted to modify an integer pointer, integer pointer, right? You just add one more star onto the type of the thing you want to change. The rule really is that simple, but even though the rule is that simple, people make mistakes with it constantly, and they either put a lot more pointers than they need, or they don't put enough pointers. Put at least one more than what you have. So if I had an integer triple pointer that my function accepted, what things would I be able to modify, or I should say, what types would I be able to modify using this integer triple pointer? A double pointer, and a single pointer, and an int, right? If I had an integer triple pointer, I could modify an integer pointer, an integer pointer, or just an int, right? There's also no more null pointer. So instead of null pointer, use null to signify that you aren't pointing anything. So over here is an example of a function where we just set our integer variable to value. So over here I have x. I pass an x's address to this function, and so I'm able to change the value to be 7. Again, if I was missing this pointer here, it's not going to work. So there's no new and there's no delete. So instead we use the functions malloc, calloc, realloc, and free. Those are all included inside of stdlib.h. You can use calloc, malloc, and free in C++ as well, but you don't want to like mix the deletes and the frees. So if you create space with malloc, calloc, or realloc, you have to destroy it using free. If you create the space using new, you have to destroy it using delete. If you mix the two together, like something created with new, and you destroy it using free, it's undefined. If you create something with malloc and you delete it using delete, it's undefined. Also, when you create something with new, that space is initialized by calling some constructor. When you create space using malloc or calloc, well, malloc it's uninitialized, realloc it's uninitialized, if it's the new space is uninitialized, and for calloc, it's all set to zeros. So you'd have to go manually set the members if you've created a struct, which is C's class object that sucks. So here's malloc. Malloc, you specify the number of bytes that you want. And malloc will create space for that many bytes. But notice it's bytes and not that many instances of the object. So everywhere you're going to be using malloc, you're always going to have some number multiplied by the size of the object, right? If I want 3 integers, I would do 3 times the size of an integer. If I just did 3, it would give me 3 bytes, right? And an integer is larger than a byte. So if I wanted like 10 doubles, I would do malloc 10 times the size of a double. Calloc kind of helps prevent those errors by splitting it into 2 arguments, the number of elements you want, and then the size of each element in bytes. So calloc is the preferred one to be using. And so if I wanted 3 integers using calloc, I would say 3, and my element size would be the size of an int. And you use the size of expression to get that. Free, you pass it a pointer, and it will delete the space that pointer points to. And that space has to be dynamically allocated using realloc, calloc, or malloc. It won't set the pointer to null, right? But it will delete the space that it points to. So you should probably, after you free this space, set that pointer to be equal to null so that you don't misuse it. So here's examples of creating some arrays over here on the right-hand side using both calloc and malloc. You have questions? Yeah. So a void pointer is a pointer to something. Correct. But if you have a void pointer, it doesn't know what it is. So you can't actually like use it to access stuff without casting it first. So because malloc and calloc all create space, and realloc too create space to just different things, they return a pointer to that space. They don't know what it is. But since you know what it is, it will be cast to the appropriate pointer. So even though malloc is giving back a void pointer here, it gets cast to an integer pointer before it's stored into P1. I'm able to treat them like integers. And again, free, since it deletes just stuff, it gets a void pointer as well. Yeah. You would generally prefer to use calloc over malloc. I think you said it the other way around. It exists. You'll see it. I mean, it's just there. I mean, like the main reason that calloc is preferred is because people forget to multiply by the size of. And so one thing that you can always do to make sure that you're getting the correct type over here on the right-hand side is whatever's over here on the left, put a star in front of it in the size of expression. So what's the type of P1? It's not a trick question. What's the type of P1? Integer pointer. So what's the type of star P1? Integer. So this says the size of an integer. What's the type of P2? Character pointer. What's the type of star P2? Character, right? So as long as you do star, whatever the variable over here is on the left-hand side, you'll always get the right expression over here in the size of. And you'll never make mistakes, and you'll never have to guess. It's always star this guy. And then again, since we have arrays, you can index the arrays just like you've done normally with the square brackets. Okay. Sorry. Don't do that to me. So Realloc is like the more complicated generalized version of Calloc and Realloc and free. I should say like malloc and free. So what it will do is you give it a pointer and you give it a new size, and it will change the size of whatever you're pointing to be that new size. But notice the new size is specified in bytes. So it's able to change the size of an array, right? Whatever you're pointing to, it's going to change the size. It can be bigger, and if you make it bigger, space gets added to the end of that array. If you make it smaller, space gets removed from the end of the array, so you keep the first couple of elements. One thing that's possible, though, is when you make a request to be a new size, there might not be enough memory right where that original pointer is located to expand to be that new size or potentially shrink. So Realloc reserves the right to move wherever your thing is at to some different area. And if it does move it, it's going to give you back a pointer to that new location. So whenever you use Realloc, you need to assign your pointer back to whatever Realloc returns to you, because sometimes it may move that stuff. And if it ends up moving it, it will delete the old stuff, and it will first it will copy the new stuff to the new location that's big enough, and then it will delete the original space. So always make sure that you reassign to Realloc. Some cool things about Realloc is if you realloc a null pointer, Realloc behaves like malloc. And if you realloc down to be 0 bytes, Realloc will free the space. So it behaves like free. It'll delete the space. Questions here? This is like one nice thing about malloc and Realloc and Calloc that new doesn't have. That you can resize arrays a lot easier. Yeah. The size of a pointer. Well, on a 32-bit system, pointers are 4 bytes big. On a 64-bit system, they're 8 bytes big. So somewhere between 4 and 8 bytes. If you're on smaller systems, the pointers will be smaller. So if you're on a 16-bit system, your pointers would be 2 bytes big. Whatever the size of a pointer is. That's how big null is. Anything else? I promise we'll get to some fun examples in a little bit where we'll do simple things that are now hard because it's C. So over here, here's some examples of using Realloc, right? So I create my original space using Calloc. So I create 3 integers. I assign them to be some value. So now I have 10, 20, 30. If I realloc P to be 5 integers, notice I multiplied by the size of. That's the easiest thing to forget. I made space for 2 more elements, right? Because I had 3. 3 plus 2 is 5, so now there's space for 2 elements. Those 2 new elements are completely uninitialized. I don't know what their values are. They're undefined. But they exist now. Right? And notice I also made sure to reassign the pointer in case Realloc had to move my memory around some of the location. Here I realloc, right, down to 1 element. So I'm going to remove all the elements except the very first one. So I just keep the 10. And then here I realloc to be 0 bytes big, so I delete everything. Yeah. If you just wanted a single element, you could do like 1 times the size of an integer. And then you can just do like star P, which gives you the first element, or P bracket 0, which also gives you the first element. So yeah, you use it to create both arrays and individual elements. Yeah. Okay, so again, the size of, it calculates the size of the type of the expression. So take this, like, literally, like, how many elements the array points to. So if I do the size of P over here every single time, what's P's type? So P's type is integer pointer. The type of star P is integer. So this is the size of a integer. This is the size of a integer. This is the size of a integer. It's always the exact same thing. If I do the size of P, that's going to be the size of. So if up here, like after I do this line right here, the first line, and I ask for the size of P, how big is it? I got 12 3-pointers, right? So sure, same thing. If I do it after I do this line, the size of P is. My mouse is right here. So after we do this line right here, where we realloc to be 5 elements, the size of P is. We have 5 pointers here. 1 pointer here. No pointer, 0. That's wrong. But it's what people think, right? And it's a really, really easy way to understand what size of does, right? So remember, size of evaluates the type of the expression, right? So P, the size of P is the size of whatever P's type is. So the size of P is the size of a integer pointer, right? So the size of P after every single one of these lines is exactly the same. And it's the size of 1 integer pointer. It's not different. It will not tell you how many elements are in your array. Never use size of to figure out how many elements are in an array. You'll be disappointed every single time. Most of the time it's going to be wrong, and you're going to end up being very, very sad. And you're going to be like, why is this not working? It's because size of tells you the size of that type. And the size of an integer pointer is always the size of an integer pointer, no matter how many things it points to. We could do, again, this is like the size of an integer here. But yes, we could just do size of an int. That'd be fine too. Any questions here? Yeah. Again, it's the size of the type. P's type is, so when you do size of P, you get the size of an integer pointer. If you do the size of star P, you get the size of an integer. On some systems, those are the same. On some systems, those are different. So this depends on how big in bytes that thing is. Any other questions? Okay. So some common mistakes are, again, forgetting to multiply by size of, forgetting to reassign the pointer returned by Realloc, forgetting to delete the dynamically allocated memory that you point to, and I guess we should add in that, that third thing that we just talked about today. I mean that size of will give you the number of elements in an array. It doesn't. It gives you the size of that type. So over here, right, we made space for 3. We probably spent space for 3 integers, but we made space for 3 bytes. It's not going to fit any integers. So we're probably going to get some fun segmentation faults or undefined behavior if we try to dereference this pointer. Here we realloc P to be 500, but again, it's 500 bytes, not 500 integers. Also, we forgot to assign P here. P should be equal to the realloc because it's very possible and super likely that this location in memory got moved somewhere else because it's so much bigger than the original. And now we don't have a pointer to like valid memory anymore because it's off in some other location. And again, we didn't free this space, so again, that would also be an error. So watch out for these. I promise you'll make almost every single one of them in your lifetime. I know I have a lot of times. So there aren't any vectors anymore. There are only arrays. Arrays are like vectors. We've already worked with them in C++, except again, they're next to each other in memory, but there's no methods defined on it, but the square brackets exist. You can allocate memory again using malloc, calloc, or realloc. If you know the size at compile time, you can also statically allocate it by doing type var name size, and you'll create an array with that much size. So here's how I could dynamically allocate space for 3 integers. Here's how I could statically allocate space for 10 integers. The static allocation I can't resize. It's stuck at being 10. So if the user now enters in more than 10 integers, I'm hosed, right? As long as they enter 10 or fewer integers, things are cool. You can also have multi-dimensional arrays. Statically, the way that you allocate them is type, variable name, the size of dimension 1, the size of dimension 2, the size of dimension 3. They keep going for as many dimensions as you have. And it's going to create a dim1 by dim2 by dim3 by whatever matrix. If you have a function, though, that accepts a static multi-dimensional array, that function has to specify the size of every single dimension but the first. And this size must be known at compile time. What this results in is you having to write a ton of the same function, one for each different size of that array that could happen. So over here, right, we have 2 functions that both print 2D arrays. But this function over here can print 2-dimensional arrays that have any number of rows as long as there's only 3 elements per row. And again, we just loop through each of the elements, printing them out. This function down here, though, it can print arrays, that have any number of rows, but have 4 elements per column. And the code is exactly the same. So you're really sad if you're using static arrays and you have to pass them the functions, because there needs to be 1 for each different size of function you're writing. And you're kind of stuck writing an infinite number of functions then, unless there's only like 1 size. So you're probably not going to want to be using static arrays, even though they exist. Does that make sense? It might not make sense right now why this is a restriction of the C language. Like, why the hell would I have to? Why don't I have to do the first one, but I have to do all the other ones? And it's because of how C allocates the memory for these arrays. Come back in ECS 50, and I'll tell you why it does it this way. And you'll understand why that has to happen. Or you can stop by office hours. Now finally, and then I'll let you go, is dynamic arrays. So you can dynamically allocate multi-dimensional arrays, and they're going to function like arrays of arrays like you've been working with before in Python, like lists of lists, or in C++, vectors of vectors. 1 star per dimension. But notice that this just creates that single variable, that single pointer, and you're going to have to go through and dynamically allocate space for all the interior elements. So over here on the right, I'm going to make a 3-dimensional array that's D1 by D2 by D3 big. So the first thing that I do is I allocate space for each of my double pointers, and I want D1 of them. Then for each of those double pointers, I make space for the single pointers that they point to. I do right here. Then for each one of those single pointers, I allocate space for the actual integers. And then I'm able to return it. So again, I still had to allocate space for each of the elements in the interior. And when I would go to delete them, I'd want to delete them from the inside out. So delete each of the elements, then delete each of the single pointers, delete each of the double pointers, and then I could, delete the triple pointer that I have. So you do it in backwards. We're going to see lots more examples of this stuff coming up because we got 2 weeks to keep talking about C.